Okay, let's unpack this. We're going deep today, really deep, into how light and matter get along, or sometimes how they collide.
Specifically, we're talking about Compton scattering. You might also hear it called the Compton effect.
That's the one. It's a concept that, well, it goes back about a century now.
But it's absolutely not just history.
Mhm.
It fundamentally reshaped how we see light. And, physicists are still using it on the front lines today.
Exactly. We've sifted through quite a bit the original physics, some modern experimental proposals, and our goal, our mission for this dive is pretty straightforward.
We want to get to grips with what Compton scattering actually is.
Right, and why it was such a game changer back in the day.
And, crucially, how scientists are using this, 100-year-old idea right now to poke around inside protons and neutrons. It's quite the tool.
It really is. It connects the dots from the very birth of quantum ideas to, well, the cutting edge of nuclear physics.
So where's the starting point? The basic interaction.
Yeah, the core phenomenon. What actually happens?
Okay, so picture a photon, but not just any photon. We're talking high energy here. Think X-rays, gamma rays, real packets of punch.
Got it. Energetic light.
And this photon comes along and interacts with a charged particle. Usually we're talking about an electron, maybe one that's not too tightly bound up in an atom, sort of quasi-free.
Like a little light projectile hitting an electron. Is that too simple?
No, that's actually a pretty decent mental image for what happens next. The photon essentially bounces off this electron, it scatters.
Okay, it scatters, but something changes, right? It's not just a simple bounce.
Exactly. The photon transfers some of its energy to the electron. So the electron gets a kick, it recoils, flies off with more kinetic energy than it had.
And the photon, having lost energy, what happens to it?
Well, a photon's energy is tied directly to its frequency and inversely to its wavelength. Less energy means lower frequency.
Which means a longer wavelength.
Precisely. The scattered photon comes out with a longer wavelength than it went in with.
And this is the core of what Arthur Holly Compton discovered back in, 1923?
That's him. 1923. He was doing experiments firing X-rays at targets like graphite materials with light elements.
Okay.
And he had detectors set up all around to catch the X-rays that scattered off at different angles. Now, the old way of thinking, the classical wave theory of light,
What did that predict?
it predicted the scattered X-rays should have exactly the same wavelength. The wave should just, make the electrons wiggle and re-radiate light at the same frequency.
But that's not what Compton saw.
Not at all. He clearly measured that the scattered X-rays had longer wavelengths. They'd lost energy.
And it wasn't just random.
No, that's the key. The increase in wavelength, what we call the Compton shift, it depended very precisely on the scattering angle. If the photon just glanced off at a small angle, the shift was small.
But if it scattered way back, a large angle.
And the shift was much larger. This angle dependence, well, it just didn't fit the wave picture at all.
And he managed to capture this in an equation.
He did. A beautifully simple one, really. The change in wavelength, let's say lambda prime, for the scattered wavelengths minus lambda, for the initial, equals a constant term times 1 minus the cosine of that scattering angle, theta.
Okay, lambda prime minus lambda equals something times 1 cos theta. What's that constant term? It involves fundamental constants, right?
It's Planck's constant h divided by the mass of the electron, m sub e, times the speed of light, c. So h over mec.
Ah, the Compton wavelength of the electron. I remember that.
That's the one. It's a fundamental length scale associated with the electron, super tiny, about 2.4 picometers, so 2.4 times 10 to the minus 12 meters.
And the formula tells you the maximum shift happens when cosine theta is minus 1.
Exactly. Scattering straight back 180 degrees. Cosine of 180 is minus 1, so 1 minus minus 1 is 2. The maximum wavelength shift is exactly twice the electron's Compton wavelength.
So the geometry of the collision dictates the energy transfer. It's very mechanical almost.
It is very particle-like and completely different from the classical wave prediction.
Now, you mentioned the electron gaining energy. Is the reverse possible? Can the photon gain energy?
Yes, it can. That's called inverse Compton scattering. It happens under specific conditions, though.
Like what?
If the electron you hit is already incredibly energetic, maybe it's moving close to the speed of light, perhaps accelerated in some astrophysical object, like a quasar jet or a supernova remnant.
So a super-fast electron hits a photon.
Or rather, a photon hits a superfast electron. In that case, the electron can actually transfer some of its huge kinetic energy to the photon during the scattering.
Ah, so the scattered photon comes out with more energy.
Exactly. Higher energy means higher frequency, shorter wavelength. It's the same fundamental interaction, just
Mm.
the energy flow is reversed because the electrons started out so energetic. We see this process happening out in the cosmos.
Okay, that makes sense. So we have the mechanism, the wavelength shift, the angle dependence. But why was this such a pivotal moment? Why did it rock the physics world, as you said?
Because it gave really, really strong evidence, you might even say undeniable proof at the time, that light doesn't just behave like a wave.
It also behaves like a particle.
Precisely. Like those quanta of energy that Einstein had proposed earlier to explain the photoelectric effect. Compton's work showed these light quanta, these photons, don't just carry energy, they also carry momentum.
And they collide with electrons like tiny billiard balls.
That's a very common analogy, and it captures the essence of it. The photon hits the electron, transfers energy momentum, the electron recoils, the photon scatters off with less energy and momentum. It all perfectly obeys the conservation laws, just like a particle collision.
Whereas the wave picture just had the wave sort of washing over the electron.
Right. The classical Thomson scattering model, which worked okay for low-energy light, predicted the electron would oscillate and re-radiate, but the wave itself wouldn't fundamentally change its character, its wavelength, in this angle-dependent way. Compton's results blew that out of the water for X-rays.
So it really cemented this strange new idea of wave-particle duality.
Absolutely. It was a cornerstone in building the framework of quantum mechanics. A huge step.
And it earned Compton the Nobel Prize.
It did in 1927. A well-deserved recognition for changing how we understand light itself.
It also helps to place Compton's scattering in the grand scheme of how photons interact with matter depending on their energy.
That's a good point. You can think of a spectrum of interactions. At very low energies, radio waves, maybe microwaves, photons mostly just scatter elastically without losing energy, or they might excite atomic or molecular rotations and vibrations.
Then as you go higher in energy, visible light, UV.
Then you get into the realm where the photoelectric effect becomes dominant. This is where the photon gets completely absorbed by an atom and all its energy goes into kicking an electron right out of the atom. The photon just vanishes.
Okay, so absorption and ejection, that's the photoelectric effect.
Right. But keep cranking up the energy. Hard X-rays, gamma rays. This is Compton's territory. The photon has way more energy than the electron's binding energy, so it tends to scatter off the electron rather than get absorbed.
This is where Compton's scattering is the most likely thing to happen.
In a broad and very important energy range, yes. But if you go to even higher energies, say above roughly 1 MeV, that's million electron volts.
What happens then?
Then a new process becomes possible, especially if the photon interacts near the strong electric field of an atomic nucleus. It's called pair production.
Pair production, creating particles.
Exactly. The photon's energy converts into mass, according to EMC squared, and creates particle-antiparticle pair, typically an electron, and its antimatter counterpart, a positron. The photon disappears and matter appears.
Wow. So photoelectric effect at lower energies, pair production at very high energies.
And Compton scattering is the dominant player in that significant middle ground. That's why it's so important in fields dealing with X-rays and gamma rays, medical imaging, radiation therapy, astrophysics, nuclear physics.
Right. Okay, so it's key for photon-electron interactions, but you hinted earlier that scientists are now using it to look inside things like protons and neutrons. How does that work? That seems like a big leap.
It is a leap, and it's where things get really fascinating and experimentally challenging. Instead of just scattering off essentially free electrons, scientists fire photons at protons, or neutrons, nucleons we call them, or even light nuclei like deuterium or helium-3.
So the same basic idea, photon scatters off something, but the something is much more complex.
Exactly. A proton isn't just a simple point particle like an electron, relatively speaking. It's got internal structure. It's made of quarks and gluons, held together by the strong force.
And Compton scattering can tell us something about that structure.
Yes. By carefully measuring how the photons scatter their energy, their angle, maybe their polarization, we can learn about how the internal structure of the nucleon responds to the electromagnetic probe of the photon. We measure properties called polarizabilities.
Polarizabilities, like
Yeah.
how much the particle gets sort of deformed or stretched by the photon's electric and magnetic fields.
That's a great way to put it. The electric polarizability tells you how the charge distribution inside the nucleon rearranges or stretches in response to the photon's electric field. The magnetic polarizability tells you about how the internal currents, or magnetic moments, respond to the photon's magnetic field.
It's like testing the squishiness of the proton or neutron.
Kind of. It
Yeah.
tells us about the dynamic response of the quarks and gluons inside. And perhaps even more interesting are the spin polarizabilities.
Spin polarizabilities.
Yeah, these tell us how the distribution of spin inside the nucleon, the way the quark spins are aligned, responds when the photon interacts with it. Measuring these gives us really sensitive tests of our fundamental theories of the strong force, like quantum chromodynamics or QCD.
So Compton scattering becomes a tool to sort of take an electromagnetic snapshot of the nucleon's insides and how they react.
A dynamic snapshot, yes. But it's incredibly difficult.
Was that?
The probability of a photon scattering off a nucleon in this way, especially if the energies needed to cleanly probe these polarizabilities, say below a few hundred MeV, is tiny. The cross-section, which is like the effective target area for the interaction, is really, really small. We're talking maybe 1,000,000 times less likely than scattering off an electron.
Whoa. So how on earth do you measure something that rare?
You need brute force, basically. First, you need an incredibly intense beam of gamma rays. Facilities like the high-intensity gamma source, HIS, at Duke University are crucial. They generate gamma rays by essentially having high-energy electrons collide with a powerful laser beam. It's inverse Compton scattering, actually, used to make the beam.
Using the effect to study the effect. Okay, so intense beam. What else?
You need detectors that are extremely efficient and cover a huge area around the target to catch as many of the very few scattered photons as possible.
What are these detectors like?
Often large arrays of scintillating crystals. Sodium iodide, Ni, is common. When a gamma ray hits a crystal, it creates a tiny flash of light, which sensitive photodetectors pick up. You might arrange hundreds of these crystals in a sphere or dome around the target.
I saw a mention of a nickname, the egg beater.
Chuckle slightly.
Yeah.
Yes, sometimes the support structures for these large arrays can look a bit like that. It gives you a sense of the scale and complexity. HINDA is one proposed large Ni array.
Okay, so intense beam, big detectors. Is that enough? Especially for those spin polarizabilities you mentioned.
Often, no. To really tease out the spin effects, you need more sophisticated techniques. You might use a polarized photon beam.
Polarized, meaning the light waves are all aligned in a certain way.
Exactly. Their electric fields are oscillating in a specific plane, or maybe they have circular polarization, and/or you use a polarized target.
You can polarize protons and neutrons.
You can polarize nuclei that contain them, yes. For example, with helium-3 targets, you can use lasers in a technique called spin exchange optical pumping to get a significant fraction of the helium-3 nuclei aligned with their spins pointing in the same direction.
And why does polarization help?
Because the scattering probability, the cross-section, can depend on the relative orientation of the photon's polarization and the target spin. By flipping the beam polarization, or the target polarization, and measuring the difference in scattering rate, what's called an asymmetry, you can isolate the effects that are sensitive purely to the spin structure, spin polarizabilities.
That sounds incredibly tricky, and you can't just use a target of free neutrons, right? They're unstable.
Correct. Free neutrons decay in minutes. So physicists use nuclei like deuterium, that's heavy hydrogen, 1 proton, 1 neutron, or helium-3, which has 2 protons and 1 neutron. These act as effective neutron targets.
How does helium-3 help with the neutron?
It's quite clever. In helium-3, the spins of the 2 protons tend to pair up and cancel each other out most of the time. So the overall spin of the helium-3 nucleus is dominated by the spin of the single neutron. It's not perfect, but it makes helium-3 a really valuable way to get at the neutron's properties.
So you scatter off helium-3 and assume you're mostly seeing the neutron's response.
With careful theoretical corrections, yes. Often these are done in what's called quasi-free kinematics, where you look for scattering events that look like the photon hit a single nucleon inside the nucleus, almost as if it were free.
And sometimes you detect more than just the scattered photon.
Right. You can do coincidence experiments. You detect the scattered photon and the recoiling nucleon, for example, scattering gamma rays off helium-3 and detecting both the scattered gamma and the ejected neutron-3 heat. They might use special neutron detector arrays for that, like one nicknamed the blowfish.
Egg beater, blowfish. The experimentalists have fun with names.
It reflects the creativity needed. But underlying the fun names is extreme precision. These experiments are plagued by potential systematic errors. You have to know your beam intensity, your detector efficiencies, your target thickness to incredible accuracy.
How do they image that?
Constant calibration. Using radioactive sources like cesium-137 or cadmium-109 that emit gamma rays of precisely known energies to calibrate the detectors. Carefully measuring the beam. sometimes rotating detectors or swapping their positions to average out any small differences between them. It's painstaking work.
It sounds like pushing the absolute boundaries of measurement.
It really is. But the results are vital. They provide really tough benchmarks for our theoretical understanding of nucleons. Theories like effective field theories, or EFTs, and direct calculations using lattice QCD, these aim to predict properties like polarizabilities from first principles. The experiments tell us if the theories are getting it right.
So what are some of the big questions or debates these experiments are tackling right now?
Well, one major focus is pinning down those neutron spin polarizabilities. There's one specific combination, the backward spin polarizability, gamma pi, where previous experiments have given conflicting results.
Different labs getting different answers.
Yes, experiments at places like LEGS at Brookhaven, the TAPS collaboration at Mainz, and others, their results for the neutrons gamma pi don't quite agree with each other within their stated uncertainties.
That's a problem.
It is. And some of the results also seem to disagree with predictions from well-established theoretical frameworks like chiral perturbation theory. So there's a real push for new, higher precision measurements using polarized beams and targets like polarized helium-3 to resolve these discrepancies.
And the ultimate goal is more than just that one number.
Oh, yes. The hope is to eventually measure all four of the fundamental nucleon spin polarizabilities. They're usually called gamma 1, gamma 2, gamma 3, gamma 4, independently for both the proton and the neutron. That hasn't been fully achieved yet and would be a major milestone for understanding nucleon structure.
What about the nuclei themselves, like helium-3 or helium-4? Are there questions there too?
There are. Even something as basic as the electric polarizability of these light nuclei is still debated. Different ways of measuring it, like scattering electrons off heavy nuclei versus looking at how the nucleus absorbs photons, seem to give slightly different answers for helium-3 and helium-4. And these also don't perfectly match theoretical calculations.
So direct Compton scattering measurements on these nuclei are needed.
Exactly. Proposals exist to do just that, scatter photons directly off helium-3 and helium-4, and measure their polarizabilities unambiguously to resolve these tensions.
It really underscores how complex even these seemingly simple nuclei are. And it takes a huge effort, right?
Massive effort. These experiments involve large collaborations, scientists from many institutions, and rely on major national facilities. And they need a lot of beam time. We're talking hundreds, sometimes thousands of hours, to collect enough of these rare scattering events to get statistically significant results.
So it's incredible. What started as Compton showing light acts like a particle a century ago
Is now this incredibly refined tool that lets us shine a light, quite literally, into the heart of protons, neutrons, and nuclei.
It's really a powerful demonstration of how fundamental discoveries keep on giving by pushing the limits of measurement for this seemingly simple scattering process.
We're testing the very foundations of our understanding of matter and the forces that govern it. We're constantly refining that picture, finding new puzzles, testing new theories. It's how science progresses.
It really makes you stop and think.
It does. You know, when you consider the sheer complexity, the years of effort, the ingenuity required just to measure how a photon bounces off a neutron with enough precision,
Oh,
it makes you wonder,
wonder what?
what other geek secrets, what other fundamental properties of this subatomic world are just waiting there, hidden from view, until we can figure out the next incredibly challenging, intricate way to measure them.